Well, welcome. This video starts chapter on wind energy. So in this chapter, we're going to be covering the basic different types of wind turbines that are out there. We're going to go over the basic science, the fluid mechanics and science behind how they work, and we're going to cover a series of example problems and then finish off by looking at some basics of controls when it comes to wind energy. So let's go ahead and get started. Basically, wind turbines can be split into two different basic classes. One would be horizontal axis wind turbines, or HAWT. Sorry. Again, these are turbines where the axis of rotation is parallel to the ground. Second class would be vertical axis wind turbines, or VAWT, again where the axis of rotation is perpendicular to the ground. Here are some quick examples of some commercial wind turbines. Here is a Mitsubishi 600 kilowatt turbine on the left-hand side of this chart. You can see that, again, it is a pretty large, pretty tall tower. So if you can kind of look here, if you make out, here is a person standing in terms of how scaled it is next to the turbine. You can see how huge it is in comparison to its size. Here's another example of a horizontal axis turbine. One is 1.5 kilowatt Berge. These are smaller scale ones. You can find things of this sort that might be used for houses and residential homes, or supplement powered residential homes. Here is another one, which is basically meant for even lower power application. Here's a schematic of a horizontal axis wind turbine, and it's just some basic nomenclature associated with it. So you can see here, this is called the tower, and the turbine is held on top of the tower inside a nacelle. Again, on the turbine itself, these are rotor blades that come out of the turbine. The height between the axis of rotation and the ground is called the hub height. As the turbine spins, the blades spin, it encompasses a certain area, right? And that area is called the sweep area. The sweep area is just simply the rotor diameter taken into account, calculating the area based on the rotor diameter. So let's go ahead and get into some basics. So the first thing that's obvious, it should be obvious to engineers in terms of what wind turbines do, is that they convert kinetic energy, the kinetic energy of flowing air, into electrical energy by use of a turbine that turns a generator. Now, the question that I always pose in this start of this part of the chapter is how much energy does the wind possess, and how much can be converted into electrical energy, right? Obviously, we talked about the fact that the power has to do with the kinetic energy, right? So 1/2 m dot v squared, where m dot is flow rate. So if we take the flow rate and compute it by the density of air multiplied by the sweep area of the turbine multiplied by the velocity of the air, we make that substitution into our power equation, we get that the power associated with the flowing airstream is basically a function of the wind velocity to the third power. So this power in the air increases dramatically with increasing airspeed. But the question is that how much can actually be extracted, right? How much energy can be used? So out of that total power in the air, how much can be used? And that's what we're going to address in the next several slides. There is a way to quantify that, and the way to quantify it is done by what's called a Betz analysis. And the limit to how much energy you can pull from the air is quantified by like the Betz limit. So let's go ahead and do a Betz analysis, right? So we're going to start first. Let's define what the actuator area is, right? So we go ahead and just do that pi divided by 4 times the rotor diameter squared. And again, that's what we would call the actuator area. So let's look at this. You have some basic diagrams on the left-hand side of this slide. Let's go through each one just to kind of explain where we're going with this. This top one, A, represents the pressure distribution as you approach the turbine and as you go away from the turbine. You can see that the pressure starts to increase as you approach the turbine. Wind hits it, you have a dramatic pressure decrease, and then as you go further out from the turbine, you can see the pressure approaches atmospheric again. So this pressure difference occurs across the actuator. What's reflected with that is the velocity, right? You have the velocity coming in. As the velocity approaches the turbine, it goes down, and then if you go far out from the turbine, the velocity reduces to some lower velocity. That's called a velocity distribution. So let's go ahead and say that the incoming wind speed is quantified as C. Okay, so C is our incoming wind speed. As we come in, we know that the wind speed decreases to a certain point when it hits the turbine. We're going to call that 1 minus C multiplied by 1 minus A. A is some sort of, we'll just say, airspeed reduction parameter. And then as you go further out from the turbine, you can see that the wind speed continues to decrease. And then we'll say that far out from the turbine, we have C. The wind speed would be C multiplied by 1 minus B. So again, just take that same graph from the prior slide and we'll put it here. I'm going to go ahead and I'm just going to define some terms. We have P1, right, the pressure, the static pressure just before the actuator, just before the turbine, and then P2, again, is the pressure just after the actuator. And again, we're going to define C as the wind speed coming into, from afar, coming towards the wind turbine. And again, let's go ahead and recast our available power. So the total available power in the wind, according to the prior slide, we derived as 1/2 density times actuator area times wind speed cubed. So what I'm first going to do is I'm going to go ahead and again, I'm going to apply, as we did in the prior slide for hydroelectric power, I'm going to apply Bernoulli's equation. So we're going to apply Bernoulli's equation at a point upstream and downstream to the actuator. So if we go ahead and do that, we can know that upstream would be at a point, we're going to call this point E, which is entering into the actuator, and point 1 when it hits the actuator. So I'm going to call this applying Bernoulli's equation between point E and point 1, the upstream to the actuator, and downstream to the actuator will be applying Bernoulli's equation between point 2, which is just after the turbine, to point O, which is some point way outside the turbine. So if I apply Bernoulli's equation to those 2 points, this is what I'm going to get. So there it is. Again, these 2 equations that were just written out represent Bernoulli's equation applied 2 times. The first time being at a point far from the actuator to the actuator, and then another time from just after the actuator to way past the actuator. So if I take those equations and I solve for the pressure difference, and then I add the equations together. So if I go back and I take these equations and I solve for delta P, right? Those 2 equations are solved for delta P each. And then I add the equations together. I'm not going to go through all the algebra, but if I do that, I end up with the following. So this is the resulting equation by basically taking those two primary equations, solving for delta P and adding them together. Now, I can go ahead and compute the thrust on the turbine by taking the pressure difference and multiplying it by the actuator area. And by doing that, I get the following. So this is, again, the resulting equation for the thrust on the actuator. Now, I can go ahead and I can equate that. I can set the axial thrust equal to the change in axial momentum. So setting the axial thrust equal to the change in axial momentum, I will get the following. And if I go ahead and I take these two equations and I can solve for A as a function of B, again, where A and B are factors that help quantify how much the velocity coming in from afar from the actuator is getting reduced, right? So again, this factor A is basically a parameter to help compute the reduction in air velocity just at the actuator. And then B is a parameter that helps to quantify the reduction in air velocity far from the actuator. And from this analysis, I'm able to set that A is equal to half B. If I were to continue this, I can quantify that. I can go ahead and say that my change in kinetic energy of the air, right? Change in kinetic energy being, again, across the actuator. This would be the change in kinetic energy across the actuator, V1 minus V2. I can go ahead and this equation will, if I make the substitutions, will result in the following. Now, what I want to do is that I want to look at the maximum change in kinetic energy. Again, this change in kinetic energy across the actuator would represent how much energy I'm taking away from the air that can then be put into converting that kinetic energy into electricity by means of a generator. I'm going to go ahead and I'm going to take the derivative of the kinetic energy with relation to A and set that equal to 0, right? And if I do that, my derivative becomes the following. And what I can do at this point is go ahead and find that A is equal to 1/3. So for A equaling 1/3 and knowing that A equals B over 2, I can state that my maximum power that I can extract from the air, if I make my substitutions back into my power equation, is 8 over 27 rho A C cubed. Now, how does that relate to the limit? Well, let's go ahead and I'm going to introduce a parameter called power coefficient. A power coefficient is like an efficiency used for wind turbines. So I'm going to go ahead and power coefficient is defined as the power extracted divided by the energy in the air, right? So the energy in the flowing air is 1/2 rho AC cubed. And in this case, my maximum power extracted is going to be 8 over 27 rho AC cubed. That divided by 1/2 rho AC cubed. So this power coefficient, again, which is quantified as the maximum power coefficient that I can extract, is ends up being 0.5926, and that number is regarded as the Betz limit. The Betz limit, again, is the maximum power that can be extracted from the air, theoretically. So with that in mind, I mean, you can see, for example, this graph gives an idea of how that works. So I have on the y-axis my power coefficient, and on the x-axis, I have something called an advance ratio, right? Advance ratio is just basically a parameter that takes into account the rotational speed. So radius times the angular momentum, the angular speed of the rotor, right, which is basically the tip speed, right? So that would be the tangential speed of the tip of the rotor. So r omega divided by the velocity of the wind. So you can see here we have several different types of turbines that are laid out. Here's the Betz limit, right, just shy of 0.6. And you can kind of see as the wind speed, as the advance ratio increases, you can see how that affects the efficiency performance of these various different types of wind turbines. And as you can see, there's an optimal advance ratio, where if the advance ratio increases past that, the power coefficient decreases below, if the advance ratio increases past or below a certain point. All right, so at this point, we'll go ahead and stop the first video for wind power, and we'll start the next video with an example problem. Thank you.